Hello and welcome to this PIR live event webinar brought to you by Partners in Research Canada. My name is Stacey Joyce and I will be your host. Remember, if you're joining us live, that you can ask questions anytime throughout the webinar using the chat button in the top left corner of your screen, and just making sure that you change the to field so that it includes all attendees as well as panelists. That way our audience will be able to see what other questions are being asked from where else in the country while we do this live today. Today's guest is Dr. Aaron Langille. He is a master lecturer in computer science and video game design at the Department of Mathematics and Computer Science at Laurentian University. Thanks so much for joining us today, Aaron. Is there snow where you are in Sudbury?
There absolutely is snow where we are. It snowed all night, and we basically went from a completely gray city to a completely white city in about 12 hours.
So visually, I think that's probably better, yeah?
It's fantastic.
Well, why don't we talk about some other worldly things and relate them to computer science, and I'll let you take it from here.
I think that's a great plan. I'm going to help out just a little bit with the hellos, and I'm going to say hi to all of the students from Powassan, which I think was the one that you were working on sort of at the beginning. So a shout out to everybody tuning in from Powassan. And with that, I will start my screen share and make sure this works properly.
Perfect. And we just got one last hello in here while you're doing that. Please go ahead. We have friends from Comox who've joined us before. They're back. Welcome to Ms. Smith's class in Comox, BC.
Wow, this is kind of almost coast to coast here, so that's pretty exciting. Today, what we're going to talk about very briefly, we don't end up with a lot of time. So with the time we do have, we're going to talk a little bit about coding. So with this being Computer Science Education Week and tying it in with the Hour of Code, it's a great time to talk about all of the different things that computer scientists do with code, whether it's computer scientists or programmers. So that we're gonna take a look at some of the more interesting ones today, and then we'll field our questions. So I like to start off with sort of acknowledging the importance of hardware when we're about to do programming. So whether or not you're going to program for a desktop or a laptop or a cell phone or a game console like the Switch or the PlayStation or the Xbox, these are all of the things that we very commonly associate with computer code. So they're the ones that when people go into programming or into computer science, they're the ones that people usually have in mind. But sometimes it's easy to forget just how many different things run off of computer code. And while I don't really have enough space on the slide to show all of them, you know, we can sort of expand our minds a little bit as to what requires computer code. Like cars nowadays have a lot of computer code in them, and there's a little animation of the SpaceX landing on the barge that happened not too long ago. And all of these things require programmers and computer code in order to function properly and safely. So, you know, this is just a little sample of what computer code might look like. This is an example of Java. So that's a language that maybe some of the students that are listening today are familiar with. If not, it might be something they're familiar with when they get to high school. But that's what a little piece of code. I'm sorry, I have to back up. That's actually C++. I'm so used to writing in Java that I see other code as if it were Java, but that's actually C++. And that's a language that we teach here at Laurentian in the second year. So moving on, I want to take a quick look at something called an algorithm. So it's not really at computer code yet, but if I'm gonna hang on for just about 30 seconds and see if people could think in their head what the next number would be in that sequence. So there's definitely a pattern going on. Some people might have seen this pattern before. It's a fairly famous one. So hopefully people have an idea in their mind of what that next number is. This is a set of numbers called the Fibonacci series, and what it is every number is the sum of the two numbers that precede it. So the number where the question marks goes would be 55. So if we were to extend this to a slightly more difficult problem, and if I were to ask the people that are listening today, you know, what is the 101st number? So there's only about a dozen numbers on the screen now, and it's fairly easy to calculate. But if I asked for the 101st number, that would be a much larger problem. And this is where computers really shine. They solve the things that are either too time consuming or a little bit too much for us to handle in a particular time. So if we take a look at how a computer would actually solve this problem, it would look like this. Now, I don't expect that everybody will be able to read that and understand what's going on. This is just to give an example of sort of what it looks like. So computer code, while it has some words that are kind of Englishy and recognizable in there, it certainly has a mathematics flair as well. And it takes a little while to learn, you know, all the pieces that are going on there. There's some punctuation, there's some syntax, and all in all, that little, you know, half a dozen, maybe 9 lines of code are designed to solve for the 101st Fibonacci number or the 9th Fibonacci number or any one that we asked for. Now, not all computer code looks the same, so it really depends on what device we're programming for or a number of other factors. So this is actually computer code that does the same as the previous slide, but I think a lot of people will find that to be a little bit more obscure, a little bit more complicated, and we're going to see a lot fewer words that we recognize, and yet this code does exactly the same thing. So it's important when we write computer code, and I tell this to my students all the time, that we also write what are called comments. So all of these lines that are to the right tell the programmer what they were thinking, so that when they come back to the problem a couple of weeks later to finish solving it or to run it again, that they can remember what's going on. So again, I don't expect that everybody will be able to look at that and understand sort of what the computer would have to do, but it's just gives you a visual idea of what computer code can look like. This is fairly low-level code called assembly, and our students do this in their 2nd or maybe 3rd year. So this is definitely not a language they would start out with, but it's one that's a little bit more efficient and a little bit closer to what the computer understands on its own. So the Fibonacci numbers, those ones where every number was the addition of the 2 numbers before it, is a fairly simple problem that we call an algorithm. And through algorithms, we're able to solve problems. Now, this is probably a lot more familiar to people than the Fibonacci numbers, being Angry Birds. But all of these arrows I've kind of highlighted have problems that need to be solved. How far back are we going to pull a slingshot? And at what point are we going to press the button so that the bird either splits into 3 or goes faster? And you know, what's going to happen to the tower when the bird hits it? All of these particular problems need to be solved with their own kind of algorithm or computer science recipe. So what we do is we write in the physics of gravity and the physics of colliding, and through processing all of the numbers very, very quickly, the computer is able to solve all of the problems that we've put in front of it. So that's just an idea of where some of these algorithms can come into play when we're not doing things like solving for the 101st Fibonacci number, which, to be honest, is a slightly dry problem anyhow. Here's another game that we tend to play in class. Maybe I shouldn't say that we play games in class, but I guess I should say that we do that in our game design class, so I think we're allowed. This is Overcooked, and it has the same idea as Angry Birds. There's a number of problems here that have to be solved. How long do we cook the meat for? How do we cut up the tomatoes? How do we get past that split in the kitchen? All of these can be broken down into smaller problems that we solve with algorithms. So we would end up with computer code that looked like the ones in the previous slides that would solve these particular problems. You know, how do we win the game? How do we work together? And what do we do when our frying pan catches on fire? All of those things would have special algorithms that we would solve. Oops, sorry, I went too far there. If we wanted to bring this a little bit further, I like talking about games since I do teach game design from time to time. sometimes, again, thinking about other hardware, we have to think about different problems that need to be solved. So if anybody has tried an Oculus Rift or any sort of VR, you'll know, maybe you don't know, I should explain, I guess, rather, that it actually splits the image into two images to simulate three-dimensional depth. And in order to do this, we have to constantly calculate these two angles that give you that sense that you are in sort of another reality, the virtual reality. And again, it sounds like it's a fairly complex task, and in some ways it is, but it uses the same kind of idea as solving the Fibonacci number. We break it down into small, little, solvable problems that allow us to triangulate vision and give us three-dimensional depth where there wouldn't have been three-dimensional depth before, and allows the controllers to work, and has all of the sounds tie in together. So it's all done using the same sort of principles of problem solving through computer type algorithms. If we take a look at some of the things that are kind of fresh and new, I don't know how many out there would have an iPhone that unlocks by scanning your face, but that's kind of a neat problem. And what happens with good software is we often forget that it's even running. So software is what coders write. It's basically everything that works on your phone or computer or console that is not hardware. So the stuff that you can't touch is basically software. And it's fun to play with things like phones and whatnot, and to see them unlock or whatever it is that they happen to do. And we often forget that there are a whole bunch of computer science, algorithms, and code all working in tandem, and it feels like it's just the phone doing the job. The phone, in the case of either Snapchat filters or unlocking through facial recognition, is taking the pictures that it needs, but a programmer has to come in and take that picture, and you can see with the face that it creates sort of a depth map, and how far apart our eyes are, and how forward our forehead is, and the shape of our nose, and the shape of our lips. All of that creates sort of this unique fingerprint style identification marker for our face. And so what the software programmers have to do is they have to identify all of those features and figure out how they can create that unique image in such a way that it's secure, or in such a way that when you turn your head, the Snapchat filters follow you. And so all of that is being done, again, with the same kind of idea behind the Fibonacci numbers that we saw, but more recipes, more algorithms happening faster and with a different purpose. So I thought it's only fair if I'm going to have someone else's face up, I'm not quite sure who that is, that I would throw mine up as well. So this is me playing with Snapchat filters in my office, probably about, I don't know, 20 minutes ago. I wanted to make sure that there was something fresh in the slides. And again, if anybody's played with these, it's quite fascinating to watch how the sunglasses or the bunny ears or the little cute button nose follows you no matter where your face goes. And that's all driven by software. So the hardware is taking the pictures, but it's the computer coders, the computer programmers that are making sure that they can track where your eyes are or where your nose is, and things like that. So it all boils down to code, which I think is pretty cool. Something else that I don't know how many of us have seen these. I know they're quite the rage in the States at the moment, but self-driving cars. Again, they have a lot of hardware that's absolutely fantastic and more in the range of what we would call computer engineering and just general engineering. But it's the software that really makes these things work. So if we're going to put cars on the road that don't have drivers, we have to make sure that they can identify situations that are dangerous. They need to identify when the roads are safe. So this is an example of what a self-driving car might see. So this is using a technique called LiDAR, which is very similar to radar, that gives the car sort of a depth perception of what's going on. So the boxes to the right are cars. I think you can see some trees in the middle that are dividing the road, and you can sort of make out some features. So a self-driving car has to be able to recognize when there's a pedestrian that crosses in front of it and it has to brake, or when there are cars that are maybe turning in the wrong direction or braking ahead of them. And all of that happens, again, through coding. So the hardware gives us the information that we need, and the coders put the information to work. So the programmers are the ones that make sense of everything that's being seen by the car, and make sure that the car acts accordingly. So there's still a lot of work being done on things like self-driving cars to make sure that they can recognize all of the scenarios, and a lot of that's being done through artificial intelligence and through photo and video recognition. For anybody that may be planning on going into the arts, maybe you're going to study history or English or anthropology, computers can help there too. So it turns out that a group of researchers wrote a computer program that read all sorts of texts. And by looking at the words and how they're paired together, so maybe you're a person that says like a lot, or maybe you tend to use a particular expression when you write. Computers, through their speed and their refusal to get bored at a task, will chew through things like a whole bunch of books. And what they can do in the end is they can recognize somebody's style, and by looking at the way that they pair their words and the expressions that they use. And they actually found that an old book, I have to look at the name of it, that an old book was actually written by William Shakespeare. I'll find it during the question. If anybody wants to know, I'll find it. But it was a book that people thought might have been written by Shakespeare, and through the use of computers and reading all of these books and comparing different styles, now they're relatively sure. It's called Double something or other. I'll get back to you on the actual name in a couple of minutes. So again, just because, even if you're not going into sciences or you're going to go off in another direction, computers and learning to do a bit of computer programming can really help in some of the tasks you might have to do. Tic Tac Toe is kind of a really good and quick introduction to artificial intelligence. Now, this is a game that a lot of us would consider fairly simple. And for computers, it's important for us to understand that they can't just sit down and play tic-tac-toe like we did when we were 5 or 6, you know, sitting at a restaurant and playing on the back of a menu or the placemat that they put in front of you. So we have to teach the computers how to play. And it turns out that tic-tac-toe is a small enough game that we can map out the whole win strategy. Now, this isn't all of the possible moves, but it gives you an idea of the kind of information that we can feed into a computer, and it can sort of memorize exactly what to do. So a lot of us will go for either the center square or for maybe the top corner square like it shows here really quickly because we think we can win. Well, computers can do that at an even higher level. They can anticipate your moves based on a map like this or a history when the game is really small. We can also do the same sort of thing through checkers. And again, it's all done through algorithms or computer recipes. Now, here's an example of what we might write. So this is an if statement, which asks the computer to make a decision. So this isn't actual computer code. This is something that we would call pseudocode, which is kind of a funny word for saying fake code. It's not real computer code. It's kind of virtual computer code. And it tells the computer to make a decision that if the particular top corner is empty, then go ahead and put an X in there. And if it's not empty, that's the else part, take a look at the center square. And if the center square is empty, go ahead and put an X in there instead. So what we would have for solving tic-tac-toe is a whole bunch of little decision statements like this. And that works for a small game like tic-tac-toe or even a medium-sized game like checkers, but it doesn't work very well for chess, where there's so many computations that even a computer can't remember all of them, and it has to learn as it goes. And speaking of goes, there is a game, an ancient board game called Go, and it's much more complex than Tic Tac Toe or checkers. And there was an artificial intelligence that was developed that can beat most human players. So you'll see the human champion there on the right, and then you can see the label for AlphaGo on the left. And what they did was they used algorithm techniques to create an artificial intelligence that played the game over and over and over again, looking for winning strategies. And it did this so effectively that the computer was able to beat human players. So that's a slightly complex task. It's something that requires a lot of knowledge about artificial intelligence and computer learning. But if you were to break it down into little tiny pieces, it would be very, very similar to the code that we've looked at already so far in this presentation. Something that I find interesting is using computers to look at climate. So whether it's climate change or simply trying to predict the weather next week, what we find is that computers, again, because of their lack of boredom and because of their ability to solve a lot of computations, can be put to tasks that we couldn't do really otherwise. So you'll see that this is basically pollution and air currents. So all of those lines are how pollution flows around sort of the northern hemisphere. But this is a task that would be almost impossible, if not impossible, without computers. And some of the climate work that's being done, or a model like this, uses some of the most advanced computers in the world. Big rooms just full of computers that are crunching numbers all the time, and the computers talk to each other. Not conversationally like we do, but they share data and they communicate numbers back and forth, and they help to solve complex problems like this. So this is one of my favorite examples. I'll finish the examples with something that's a little bit less interesting to look at and a lot easier to write than, say, a computer program that can beat the Go Grand Champion or climate change stuff. And this is some work that's been done by researchers in my group. And the 6 black and green rectangles that you see on the left are simulating how seeds fall from trees and how far baby trees grow from their parents and whether or not they cluster. So this is a program that was written not too long ago, and it's much simpler, but it gives us sort of a real tangible result that would be really difficult to solve using pencil and paper. The maps on the bottom show how fruit flies are expected to disperse across the United States based on climate change. And the one that's sort of off on the right is actually a simulation about how forests regrow when there's been a forest fire, or whether or not they've come in and clear cut all of the trees down. So believe it or not, all of those squiggly lines give us an idea of how a forest might regrow. So these are just some examples of problems that we solve with computer science. Some of them are a little bit cooler, like self-driving cars, but some of them, even though they lack the wow factor, are really helpful in research like forestry or artificial intelligence. And so there's all kinds of things that you can do once you learn to code. Now, learning to code, there are several options. If you're brand new learning to code, you could consider something like Python or Google Go. And as you get better, you could move up to something like Java or C++. And if you're really interested in trying your hand at video games, I would recommend Scratch, which is probably good for most of the people listening today, as well as Stencil. And once you've got a little bit of practice, you can try Game Maker or Unity, and all of these things will help you to learn to be a programmer, but it takes some practice. So my Twitter information is down below if anybody wants to reach out to me after this presentation, and I'll turn it back over to Stacy.
Well, thank you so much. We'll leave that slide up for a minute or so, so anyone who wants to copy that down will be able to do so. We first have a comment from Ms. Carrie Giannis's class saying that they're a group of grade 9s and they really enjoyed hearing about Shakespeare and coding. I think that was maybe a surprise link today. And the first, go ahead.
Sorry, I think the name was Double Falsehood. So if you want to Google Double Falsehood and Shakespeare and computers, you should find that there's some interesting articles about how they solve that problem.
Very interesting. That is not a connection that I would have expected in two different fields. Very interdisciplinary. And our first question is coming in already asking if one could use coding for hacking.
Yes. So hacking is an interesting topic. A lot of universities will teach hacking. I'm gonna do quote marks, hacking. A lot of times people will use hacking to mean using something for a purpose other than what it was intended. So, you know, hacking itself is not necessarily a bad word, but when you are using computers to gain access to resources like, I don't know, since a lot of people in our audience will be at school today, we'll say talking about gaining access to school grades or school computers, that is considered, you know, the worst thing that you can do as a hacker is to try to get to somewhere that you wouldn't be allowed to get otherwise. That is very much illegal, very much frowned upon, and it's something that you want to try to avoid. Now, having said that, when we teach security of computers, we do teach some basic hacking techniques to our students so that they're aware of what tools are available and they can test their own systems for security. So the short answer is yes, you absolutely can use computer code to hack. If it's something that you're interested in, I recommend that you talk to your teachers and have special computers set aside for which you have permission to access, and otherwise I would avoid it.
Good advice. Next we have a question from Mr. Watt's class in, I believe, Toronto, asking what are the names next to the green rectangles from your second last slide? What do they mean or stand for?
Okay, I'll back up really quick here. Those are the names of the types of plants that we were looking at. So there is an island in just south of Central America, and it's called Barrow, Colorado Island, and on there are a whole bunch of tropical plants, and we were really interested in whether or not we could reproduce the patterns of those species, and so we wrote a simulation program to do it. So on the left-hand side you see how the plants actually were, on the right-hand side you see our estimates at recreating their patterns, and way on the left are the names of those particular plant species, because each plant species had kind of a different pattern to where it was located on the island.
Very interesting. Well, I think we're okay to pull down the slides now, unless some questions come in about slides, we can always put them back up.
Good.
Brianna is a grade 7 student in Comox, BC, and she would like to know, what is the most difficult programming language to learn?
Oh my. The most difficult. I'm not sure I know enough languages that I can answer that, because I only know a handful of languages. I know them fairly well, but I only know a handful. I think I would be more inclined to talk about the easier languages to learn. There are some languages out there that are used only for very specific things. My students tend to find assembly language quite challenging, and that was on the second or third slide after I showed the Fibonacci numbers. The languages that are used for really specific programming or for really specific hardware tend to be a little bit more challenging to learn. Languages like Python or Ruby tend to be significantly easier, but they're considered general programming languages. So when a programming language can be used on a lot of hardware, it tends to be a little bit easier than ones that are used by very, very specific applications. So I don't think I could name a specific language, but definitely there are some tricky ones out there.
Right. So next we have a question about the self-driving cars. So we have a question about how they know when the traffic light changes.
That's a really good question. So not only would they have LiDAR, which is that radar-like thing that gives them sort of the depth vision, they would constantly be taking pictures, and they would be constantly recording video as well. It's fairly easy for computers to recognize colors, so they would be able to see those colors. I'm guessing also that in places where self-driving cars are common right now, that the lights may even emit a special signal that tell the self-driving cars when they can go. Because there are so many complicated problems, I would imagine that the cities that are sort of embracing self-driving cars are trying to help them out a little bit. So I wouldn't be surprised if there was a couple of cheats for the cars, like signals saying that they're green. So there's actually a handful of ways, and the easiest one that would come to mind would be taking pictures of the lights and then identifying the colors, which is something computers can do fairly easily.
Interesting. That would have struck me as something that might be difficult, but I suppose we've got, hex codes or RGB values for many colors that could be cataloged.
Yeah, absolutely. So just to follow up on that comment, all of the colors in a photograph are made up of red, green, and blue pixels, and it's actually quite easy for computers to tell, which ones are lit up. So if it can take a picture of the lights, it would know that there's a change in the brightness of the bottom light for green, or the middle light for yellow, or the top light for red. It would be able to detect those differences and know that there was a light change. So yeah, I think that one's probably one of the more straightforward things that a self-driving car would deal with. I think it's more the other complications like people and other cars that are the really tricky things.
Right. So moving on to sort of a different question, we have a question now from Ms. Hutchison's class, wondering if modding counts as coding.
So if you're referring to writing, say, mods for Minecraft or mods for video games, I would say absolutely. Anytime you're dealing with logic, or with variables, which is how we store values. Logic is how we decide whether or not we go one way or the other, or dealing with loops. You are dealing with coding. So another example that people might say, well, does this really count as coding, would be things like Scratch. So if anybody that's out there has done any video games with Scratch, I would absolutely call it coding. And coding is changing. So even though I show assembly in this presentation, which is a very complex language for people that are first starting out, there are a lot of languages that are going almost completely visual now, which is a little bit tough for people like me to get into, since I've been coding for about 25 years now, and it's hard to change. But there are languages like, if you want to Google Unreal Engine, that take boxes and connect them with virtual wires. So the whole notion of what coding is kind of changing. And I would say anytime you're using logic, or using decisions, or using loops, that you're doing some kind of coding. I often tell my students they should be coding on paper, so they don't even need a computer language to get started coding, and neither do you.
Wonderful. Now, I want to do a couple quick fire questions, and then I have a couple questions held. We're right at the end of our time right now, so we will wrap up. So first, the quick fire ones. We have a question from Ms. Hutchison's class, wondering if it's more difficult to learn to code C++ or JavaScript.
I'm going to say C++. If you're just learning, try JavaScript. It's a lot safer in terms of the things that could go wrong. JavaScript, start there. C++ can come after.
The lightning round is going well so far. Ephraim from Ottawa wants to know if you enjoy playing Minecraft.
That's actually a very tricky question that would require a whole other 15 minutes. Minecraft is an argument that my students and I have quite often, only because it's a funny game that I would call more or less a simulation. So I'm going to say I haven't played much Minecraft, not for any particular reason. I don't dislike it, but it's a funny conversation that my game design students and I have. My kids play it all the time, so I'm quite familiar with it, but I don't play it that much.
Right. And so next, getting into my last two questions that are not quite so quick fire. We have a question coming in from Ottawa. Harvier would like to know when you became interested in coding and computer science, and how long did it take you to get into your career?
That is an excellent question. I became interested in computer science through two things that happened in my life. So I was a game player, starting with a Nintendo Entertainment System. I feel like a lot of your audience might need to look that one up, but I started playing.
Maybe not. The NES Classic and
That's
the
right.
SNES Classic have been coming out.
And emulators, that's true. So I started back when I was about 8. I started playing video games and I loved them. I played Commodore 64s and VIC-20s. And when I was in late high school, I got a job at a computer store fixing computers. Between those two experiences in my life, I went into computer science. I did a 4-year degree in computer science where I learned to program, and I went off to work writing software for a few years, and then I came back to work at the university where I've been for the last 15 years. So it was games that started me on the road to computer science, but it was working at the computer store that kind of cemented the idea that I would go on to do this for a while. So it was after university that my career got started in computing.
Wonderful. Next up, we have had a couple questions come in. One from Ms. McCall's class, wondering what is the difference between a college diploma in computer science and a university degree in computer science?
I think that a lot of colleges won't call their diplomas computer science. They'll call them diplomas in information technology or information security or something along those lines. What happens in most cases with college is that you'll do a lot more applied work, and in university you'll do a lot more theoretical work. Now there are always exceptions to that rule, so anybody that's interested in either a college or a university should ask either place that they're looking to go and make sure that they're getting the right experience. But for the most part and in general, it would be the difference between being more hands-on and more theoretical. So hands-on is usually the college approach, and theoretical is usually what you get at the university. A lot of programs will have a balance of both. So again, I'm speaking in very, very general terms, and for anybody that's unsure which route they want to take, they should reach out to a college and a university and sort of get those specifics.
Well, thank you. I can't resist going back to a lightning round question that we just received from Ms. Phillips' class asking, what is your absolute favorite video game?
Oh, Mega Man. Absolutely. No hesitation. So Mega Man 2, actually, I need to be specific. And if you're really interested in the details, my second tattoo was Mega Man, and he sits up here on my arm, and about my 4th or 5th was one of the villains, and he sits on my calf. So yeah, it's definitely Mega Man. I mean, I have a list of about a dozen that I would call my favorites, but at the top is Mega Man 2, and I go back and play it usually about once a year.
It's interesting because either Ms. Phillips or someone in the class has commented, great choice right away. So definitely some approval happening.
Good.
All right. Well, to wrap things up today, I do want to ask one more question, non-lightning round, coming from Ms. Hutchison's class. Thinking from an advice perspective, to wrap us up, if you had to predict the future, what would you suggest for jobs associated with coding and computer science?
Well, what I would do is I would start by having a computer predict the future because that's what they're good at. Definitely not me. If I had to predict the future, let me talk a little bit about the past. Computer science jobs have been increasing for a solid decade or more. What was happening well back when I was probably the age of a lot of the audience members is most of the computer science jobs were for larger companies, and so you needed some experience to get in. But now what's happened is almost every business can use a computer scientist. So computer scientists are doing all the websites. They're doing the sorry, I shouldn't be so specific as to say computer scientists. I'll say programmers, because not every programmer is a computer scientist. Programmers are writing the websites. They're analyzing the data, even for small businesses. So what we're finding more and more is that unlike other industries, teaching, nursing, doctors that are very cyclical. You get a lot of a particular group in, and then it takes a break for a little while. Computer science jobs just keep going up. The salaries are very competitive. Programming jobs. Programming jobs just keep increasing in the numbers. So when I talk to students that are interested in coming to university or to colleges, I always try to reassure them that the job prospects are good. The specifics of what you would be doing as a programming grad really vary depending on what it is you like. Some of my students go into IT, which is more configuring Windows or configuring Mac laptops, or making sure that the software is running properly, or making sure that servers are running properly. Some go into very complex information security, like making sure that things are encrypted, or checking whether or not hackers are trying to get into the system. So there's a real range of jobs. A lot of them are working for local companies and doing web development. People seem to love doing web development because the jobs change frequently. So rather than working on the same thing for a long time, you get to change every few months because the websites are done and you move on. And some of my students go into game design. So there are so many jobs, and I highly recommend either as a classroom exercise or for people to do this on their own, head out to a job bank and have a quick look at, just search for programmer or coder and see what comes up. And I think people will be very surprised at just how much is out there, even not in big cities, even in smaller towns. There are a lot of jobs looking for programmers.
Wonderful. Well, that is all the time we have. Thank you so much, Aaron, for joining us and showing us such a wide spread of possibilities with computer science that a lot of our students may not have thought of before.
No problem. It was absolutely my pleasure.
And just a quick plug for next week on PIR live event. We are doing both a webinar on autonomous vehicles. Now you've gotten a little teaser for that. We'll be talking about GPS and positioning with autonomous vehicles. And we also have a webinar on December 13th for teachers. So if there are any teachers out there who want to incorporate some more computer science and coding or programming throughout your school year, we'll be talking about some practical ways to expand beyond just 1 hour of code or just 1 week to celebrate computer science education. So thank you so much for joining today. I hope you enjoy the rest of your computer science education week, and we'll see you again. Bye now.